All right, welcome back. I'm on section 1.5 discussing nuclides, and the first thing we're going to do is talk about what we ended the last lecture with, and that is ZXA notation. So I'm going to just put that Z, X, and an A. So first of all, the X is nothing more than the symbol's element. That would be the element. So if I wanted iron, the symbol for iron is Fe. If I wanted helium, it's He. If I wanted hydrogen, it's H. So that's just a symbol, and we can look all of the symbols up on the periodic table of the elements. Z represents the number of protons. The number of protons determines what element I have. For iron, it is 26. So if you have 26 protons just grab them, jumbled up in your hand right here, you've got an atom of iron. If you only have 2, you've got helium. If you've got 1, you've got a proton, which is hydrogen. And then up here, the A is the number of protons plus the number of neutrons. So up here, iron 56. That means I've got 26 protons and a total number of protons and neutrons of 56. I could subtract this number from this number, and it would give me the number of neutrons. Up here, 2 helium-4. 1 hydrogen-1, because it's got a proton and a surrounding electron. So this is ZXA notation. If you're looking on the left-hand side, there's a note. The number of electrons in an electrically neutral atom is the same number as a proton. So if I had the same number of electrons as protons, this will be electrically neutral, is what I'm trying to say in those fumbled up words, right? So let's take a look at a picture at that. If I have 2 helium-4, since I have 2 protons, if I want this atom, and I'll draw a picture of that atom, there's 2 protons, there's 2 neutrons. If I want this to be electrically neutral, it needs to have offsetting charge of 2 electrons. If it didn't, if it was missing 1 or 2, let's say, this thing would be helium, but would have a +2 charge because it's got the 2 protons, but it's missing its orbital electrons. This too is going to be something interesting in the future. That right there is called an alpha particle. Alpha particle. It is just a helium nucleus missing its surrounding electrons. Another point that we need to look at on this page. We're in section 1.6 now, isotopes. If I was to take 92 protons and I look up the symbol for that, I see that it's uranium. Well, any time I have 92 protons, I always have uranium, but I could have a different number of neutrons inside the nucleus. So let's say I have 92 uranium-234. I could subtract 92 from there and see that, well, I have 92 protons and I have 141 neutrons. Oh, bad math, 142. That would equal 234 nucleons. Well, what if I have 92 uranium and I added a neutron? Well, this number here will become 3. I still have uranium because I have the same number of protons. And I could continue. What if I had 92 uranium-239? These are all called isotopes of uranium. It's still uranium because I have 92 protons, but I just have different number of neutrons. And when there's a different number of neutrons, it will change this number up here. When we were doing ZXA notation just a second ago, we were doing ZXA notation, Z, X, A. This number of protons here, it's called the atomic number. The atomic number. This is the symbol, and it's usually a letter or two, sometimes three when we start talking the really, really heavy elements. And then this A, we said, was protons and neutrons, but it's called the atomic mass for us. On your periodic table, it may be called the atomic weight. The atomic mass is nothing more than the atomic weight rounded up. That's all it is. So you may get a number that's got a decimal point after it. You may see 26 Fe, and then you're not going to see the 56 on the periodic table. You're going to see 55.82 or something like that. I can't remember the exact atomic weight. For our purposes, we round it up to 56, and it's the atomic weight, or atomic mass rather. And we know that the atomic mass is the mass of the protons plus the neutrons. The atomic number is just the protons.